Okay, yeah, thank you, Layla. So good morning, everyone. My name is Eric. I'm a data analyst with M2M Tech, and I've been with the company for a little over 2 years now. Today, I'm really excited to present a topic on image classification, particularly within the ocean sector. So without further ado, let's go ahead and get started here. So the big goal for today is to help you all understand the basics of image classification, kind of like its history, how it works, that sort of thing, where image classification is being used in the ocean sector, and then finally how you can try it yourself with an easy, free to use online low code tool. So I hope to keep this session fairly conversational and hands-on. There's also a live demo aspect as well, like I mentioned, an interactive element, and even a chance to share how you might actually use this in your own work. Okay. So before I go and dive into all of the technical details, I want to hear a little bit from you guys. So why did you come to this session? What drew you in? Are you guys here to solve a problem or just curious about AI? Feel free to unmute your mic or type into the chat. I'm hoping to just get some engagement here early on just to get an idea of why we're here. Yeah, feel free to just speak up. Oh, that's okay. Maybe in the chat then. AI and aquaculture student, application of AI in environmental sector. Yeah, so that sounds all very relevant. So that's awesome to hear. So in terms of any workplace challenges, feel free to just share any workplace challenges that you guys may have and also what you guys are hoping to learn from using AI in your everyday life. Now, I'm going to go ahead and talk a little bit about the regional landscape. So, uh, taking a look at Vancouver, a city on the west coast of Canada, Vancouver is quickly becoming a powerhouse for AI-driven innovation in the blue economy. So, what we're seeing right now in Vancouver is a rise in sectors like port logistics, marine conservation, aquaculture, and maritime safety, all of which are actively exploring and adopting AI tools. And the really exciting part is that it's no longer only restricted to the big players and companies. You have small and medium-sized enterprises that are jumping onto this AI wave that are looking to incorporate AI into their everyday workflow. So their ultimate goal is to help maintain a focus on making AI accessible, sustainable, and inclusive for small and medium-sized companies. So one particular example is the Port of Vancouver, right? So Vancouver is Canada's largest port, so they play a big role in our ocean economy. And the decisions that they make will have enormous ripple effects. So that's why it's even more important that they make the right calls. The Port of Vancouver is using AI to optimize vessel traffic and berthing schedules. And it's not just some cool tech upgrade, right? What it directly results in is in lower fuel use, reduced wait times, and fewer emissions overall. So this is where efficiency and sustainability can interjoin together. They've also got the ECHO program, which uses AI to analyze underwater noise levels. So this helps guide real-time decisions like slowing ships to protect marine mammals from acoustic disruption. It's a perfect example of how AI isn't just about business performance, but it also places huge emphasis on ecological responsibility as well. Another example is Ocean Networks Canada. So what they do a lot is with regards to environmental monitoring. So in particular, they run marine observatories along BC's coast, including that of Vancouver. And so these observatories, they basically collect massive streams of data, whether it comes in the form of video or sound or sensor readings, and they use AI to help make sense of all the data that they collect. So for example, they use it for disaster detection, like tsunamis, landslides, and ecosystem shifts in real time. It's also used to identify species and track biodiversity, which is incredibly valuable for researchers. And the best part of it all is that a lot of this data is open source, meaning local, small, and medium-sized enterprises can actually build AI tools directly on top of it. So now moving forward onto computer vision, right? This is kind of a term that has been exploding recently, I want to say, but it's actually been around for a couple decades now. So computer vision itself, the definition is um, basically a field of AI that is focused on helping computers see, to interpret images and videos in the same way that humans do. Computer vision has been around since like the 1960s, but it's really only exploded recently, mainly thanks to advances in deep learning as well as access to massive data sets. So it's not just some futuristic sci-fi concept anymore. We have computer vision being prevalent in our everyday lives, whether it's from robots to self-driving cars. Computer vision is one of the most applied forms of AI today, whether we realize it or not. So taking a look at this picture here on the slide, we can see the similarities in concepts, right? But just using different parts to achieve those concepts. So here, the top row is for a human, the bottom row is for a computer, right? So we start off with the same object, which is a tomato, and then we kind of have the part that sees things, right? So for a human being, it would be the eye. For a computer, it's a sensing device or a camera. And then we need something to process the information that we're seeing, right, through our eye or for or for a computer through the camera. So that processor for humans would be the brain, and for, well, a computer, it would be the CPU and GPU. Once we take the visual information, we process it and make reason about it, then we reach the end result. So for humans, we don't have sort of like a probability model. Essentially, we just have a direct answer, right? If we see something, our human brain tells us that's what we see. But computers don't necessarily interpret things that way. So after a computer makes reasoning and processes what it senses, what it sees, it lists out probabilities, right? And obviously, we're not 100% certain. Computers cannot be 100% certain with what they perceive. However, they do have probability scores. Um, and as you can see here, uh, typically, you know, there would be a majority in terms of what the computer senses, right? So here you can see, for example, it lists out three probabilities with the vast majority being 84% tomato. So it is most likely correct. And that's kind of how a computer functions, right? It's based off of probability and likelihood. So you've likely already used computer vision today, perhaps without even knowing it, right? So some of the most common forms today, you can think of facial recognition to unlock your phone, right? That's a huge one that we use pretty much multiple times every single day. Or perhaps your doorbell camera pinging you when a package arrives, like your Ring camera, for example. You've also got computer vision used on social media. So for example, like those filters on like Instagram or Snapchat, those are also part of computer vision. One example that I'll show later on are Amazon Go stores. Okay, so these stores, they use cameras to track what you grab off of shelves. Tesla, right, the car company, they also use computer vision to help steer their vehicles through autopilot and FSD. So clearly, we can see just how many industries rely on computer vision. And then later today, we'll also focus on what it means for the ocean sector. So here are two images that I took myself when I was in Toronto for a layover on my way to Montreal this summer. And inside of the Toronto airport, they had this Amazon Go store. So it was my first time encountering something like this, and I found it really interesting. But essentially, for those who don't know, what it basically is, it's kind of like a small convenience store. And then uh, kind of the cool thing about it is that there are no cashiers. There's no self-checkout, there's no, cashiers. All you really need to do is just uh, enter your card information, and then it allows you to enter through the gate. You can pick out whatever you want, and then you can walk right out. So through through camera tracking, it's able to tell and watch what items you're picking, how many of them you're picking, and then, clearly it's accurate enough to the point where they're able to roll this out into everyday life. So uh, it was my first time encountering something like this. I thought it was really interesting, definitely something really innovative. And this is just one of the examples in how computer vision is going to play a bigger and bigger role in our everyday lives, right? And, you know, judging based off of this example, there's a lot of pros and cons with this situation that we see here, right? So one of the benefits could be that I'm saving a lot of time, right? Because now I don't need to go to self-checkout. I don't need to, go see a cashier. But then on the downside, it could also mean that the cashier, the job is lost now, right? Because they don't have any more cashiers working for something like this. So I imagine this is kind of the beginning where it's on a small scale convenience store level, and then maybe eventually it will reach higher and higher to like supermarket level where we go grocery shopping and whatnot. So this is just one example of how computer vision is really changing the way in which we traditionally do things as a society. All right, so now I want to talk a little bit about computer vision as kind of like an umbrella term, right? So it's not just one thing. Computer vision encompasses a whole variety of different topics. Okay, so you've got a variety of different methods. So for example, you have tools like object detection, image segmentation, localization, pose estimation, and then for our focus today, image classification. Okay, you guys may have heard of these terms floating around before, but perhaps never really fully distinguished the differences between each of them. Okay, so each of them has their own strength and weaknesses depending on what you need the AI to do. So we'll go through each of them briefly so you get the full picture, and then I'll circle back onto image classification since it's at the heart of today's workshop. So to start off, our first kind of buzzword under computer vision is image segmentation, okay, otherwise known as instance segmentation. They're synonymous. So image segmentation assigns a label to every single pixel in your image. So by that nature, it works on a very granular level, right? Since it focuses on every single pixel within your image. So let's say, for example, we show our computer an image of a cat and a dog, okay? And then we were to run image segmentation on it. So then it would color every single pixel and say whether or not it belongs to a cat or it belongs to a dog or it belongs to neither. Okay, so it's essentially outlining objects with pixel perfect precision. So it image segmentation is all about working on a granular level, trying to classify each individual pixel, whether or not it should be classified as an object, or just as not as a non-object. Okay, so image segmentation is super useful in medical imaging, satellite footage, and environmental scans where you need really extreme pinpoint accuracy. Okay, so this one is image segmentation, and you can kind of see that it basically colors, um, right, the dog here a certain color, right, blue, and then for the cat, it distinguishes it as a different object in the image by coloring it a different color, right? That's kind of how image segmentation works. The next keyword is object detection. Okay, so object detection draws these bounding boxes around the things that it spots. So then instead of operating on a very granular pixel level on every single pixel, this object detection is a bit more generalized in the sense that it would wrap an entire rectangle around each object in an image. Okay, so for example, here we have the same cat and dog example. Our classifier is able to detect and separate each object within the image, and then it would draw a different color box to identify what are the different objects in our image. Okay, so uh, object detection, this method is commonly used in things like vehicle tracking, inventory scans, or perhaps any situation where you would want to count or locate multiple objects really quickly. Okay, and then from our example here that you can see with the cat and the dog, it's also possible for bounding boxes to overlap with each other depending on the proximity and location of the objects in our image. Okay, so this one here is object detection. It has the bounding boxes as opposed to coloring each individual pixel. So the next kind of terminology is localization. Okay, so what is localization, right? It seems like it's also drawing a box. So how is it different from object detection? Well, localization is, you can kind of think of it as a precursor to object detection. Okay, so localization also draws a box, but then it only draws one. So localization is kind of like the action. It's kind of like the verb. It is the act of identifying where a key object is without breaking down specifically where the what parts belong where under that key object. So if you want to just track to see if there's a seal in your photo, you do not worry about the tail or the flippers or parts of the seal. You only care whether or not you have that certain object in your image, right? So localization is essentially the act of drawing boxes. So localization is a part of object detection. Okay. And then this one is a little bit unique and different. So pose estimation, right? This one, as the name suggests, it finds key points on a body or object. So you can kind of think of like your typical yoga app that helps to track human movement, right? Like the bends of your elbows or your knees, or perhaps you have like AI referees that help monitor athlete posture to maximize athletic performance. Okay, so that's kind of what pose estimation is about. It's using computer vision to track essentially the joints on humans, but also we can expand it to other animals as well, right? So something like this can be useful in ocean environments, like for example, if you wanted to track fin movements of like whales or dolphins, or perhaps the posture of other marine mammals, right? So that's where pose estimation can also be highly useful and effective. And then last but not least, the topic for today, image classification, right? So this is when the AI looks at a full image and just assigns it only a single label, like for example, fish or plastic. It doesn't care where in the image that particular thing is. All it really cares about is what the whole thing represents. So it's like an elevator pitch of computer vision, right? It's fast, tidy, and scalable. And it's especially useful when you've got thousands of underwater photos to sort through. So for image classification, you'll notice that, you know, it's not highlighting any pixels, it's not drawing any boxes. It just takes a single image and then tries to assign a label to it, right? So then um, the perhaps some of the pitfalls of where image classification uh, could be suspect to is if your image contains multiple objects, right? Like if I had a cat and a dog, I'm not too sure what to label it. So for image classification, you need to be really mindful of the images that you train your model with, as well as the images that you're testing with, because like I said, it's only a single label assigned to the entirety of your image. So now, just as a recap of all of the methods, we have image segmentation for pixel level labels, object detection for bounding boxes, localization is the act for general object placement, and then you have pose estimation for pinpointing joints, and with our focus today, image classification. So with our example that we see here, you can also think of it as whether or not it's a single object or multiple objects. If you have multiple objects, this is where object detection and image segmentation can be helpful for you because they are able to distinguish and segregate different objects in your photo, right? But if you only have a single object, then you would basically only rely on image classification. And then where, um, if you wanted to locate where your object is in your photo, you can also add localization to it as well. Okay, so now let's talk a little bit about why image classification is important. So mainly, especially recently, we live in a world that's swimming with data, especially visual data. I think there is a statistic somewhere saying that something along the lines of the last like 5 years accounts for like 70 or 80% of the world's data, right? So we're moving at an exponential rate in terms of the data that we're able to collect. And then it's especially important for us to make sense of what we're dealing with, right? Within the context of the ocean sector, you have things like cameras in your trawl net to underwater ROVs. All of these things are capturing more images than humans can ultimately keep up with, right? And so this is where AI can play a role. Image classification can help label those images instantly and spot trends. And then it allows us to focus more on decision making rather than data sorting. So then, how does image classification work exactly, right? So, um, to simplify it as much as possible, image classification, it essentially starts with raw pixels. These come in the form of numbers and then gets interpreted by a machine. So from there, it processes the image in layers. It tries to recognize things like shapes and textures until finally our classifier makes a decision on what the image is most likely showing. So at the heart of all of this is something called a CNN, otherwise known as a convolutional neural network. So these are very, very popular for image classification, right? So it's good at picking out patterns in visual data. It's a lot more efficient than your traditional kind of neural network. And CNNs are what lets your phone, like for example, recognize your face, right? So those like biometric authentications, or also letting AI to tell the difference between a seal and a sea cucumber. Okay, so the first step is your input, right? So for your raw image data, it gets broken down into pixel values. So these pixel values are RGB values that range from 0 to 255, right? This becomes the input for our CNN. You can kind of think of it like feeding the machine a digital canvas. So all it sees are color values and nothing else. The next step is pre-processing, right? So we might need to apply some transformations to it. We might need to resize it, normalize it, sometimes flip or rotate our image to help the model learn to generalize it. So this is known as image augmentation, right? Where we just apply a handful of transformations onto our data. So the reason why we do this, you can kind of think of it as like training a dog with pictures of tennis balls from multiple different angles. We want our dog to recognize that it's a tennis ball no matter how weird the angle of our photo is. So then the next step after we've provided our image data and then applied some image augmentation, now the step is feature extraction. So this is where our CNN begins to convolve with using filters. So essentially, um, our CNN would look for edges, shapes, and textures. So those kinds of patterns in our image that will be useful in allowing it to make predictions later down the line when it sees new images of uh, the same kind of like species or category. Okay, so to put it simply, this step here, right, is just looking for patterns. It does something called pooling, so that kind of downsizes your information while still keeping the core pieces of what matters. It looks for lines and curves. And so that's kind of what feature extraction is all about. Next step is the flattening and fully connected layers. So after extracting those patterns within our image, we flatten that data into a single vector, and then we push it through these decision layers. Okay, so that's where we have nodes that kind of make predictions based off of the numbers that we provided. So this is kind of just like you can think of it like the AI's brain deciding, trying to figure out what it just saw. So going back to that computer example with the tomato, and if feature extraction is like gathering clues, then this fourth step is like the detective making the final call. And then lastly, we have the output layer. So this is where our model just spits out the prediction of what it sees, whether or not it predicts like a fish or plastic or a boat. And then with the example that we saw earlier, each kind of uh, category or object that it predicts also needs a corresponding confidence score, right? So it needs a probability score for it to decide the highest probability, right? And then the highest probability is going to be the decision of uh, the model, essentially. So like I said, just keep in mind, behind that one word label is like a whole pipeline of multiple layer different analysis, but it only took milliseconds to run. Okay, so now I want to shake things up here and then introduce like a really, easy but fun interactive activity. So I have something here called Quick Draw. It was developed by Google AI, and it's one of the easiest ways to kind of understand image classification and how it works. Okay, so essentially, Quick Draw is a game where you are given 20 seconds. You are given a prompt, so like an object, for example, like a boat, and then you have 20 seconds to draw a doodle, and then there's an AI voice in the background that tries to guess in real time what you're drawing. And then within those 20 seconds, hopefully your drawing skills are good enough for the AI to guess what you're drawing. So it's kind of like Pictionary mixed in with a little bit of machine learning. And the cool part about this is that every single time someone draws and finishes their doodle, if they get it right, then the scribbles are added to what they proudly proclaim is the world's largest doodling data set, right? So it's very crowdsourced. And this isn't just like, just a game, but instead, your results are actually contributing to AI learning, right? Because their database is continually expanding. Okay. So I'm just gonna do like the demo here. Um, just- so you just need to search up quick draw. Okay. So this one is the page here. Um, and so yeah, like I'll just do a quick demo here so we all can get an idea of how it works. So it says to draw a computer keyboard.
I see
So
line. Or bench. Oh, I know. It's computer keyboard.
And I think you guys are able to hear the voice, right? So you can hear the AI trying to guess and figure out what it is that I'm drawing. So when I first started off those couple lines, it thought it was a bench, and then as I kept on going, it figured out that it was a keyboard. And so this is basically the game and how it works. So for
I see
here,
line.
I
Or
needed
wishbone.
to draw a
Or
jacket.
knee. Or sweater. Oh, I know. It's jacket.
It's a jacket. And then you'll also notice that um, I didn't even fully finish, right? I was only maybe like 60% of the way through, but it was able to tell from already one half of the coat that I was drawing, it was able to already assume that I was drawing a coat, right? So this one here, draw a whale.
I see garden hose. Or shoe.
Whale might be a bit trickier.
I see helicopter.
Maybe
I
I need
see
a
submarine.
smile.
Or dolphin.
Oh,
Or mouse. I see shovel. Or fish.
okay.
Sorry, I
So this
couldn't
one,
guess it.
I couldn't get it. right? It was able to guess fish, so it was pretty close, but then ultimately it was not able to guess the whale. Now draw a harp. Okay.
I
Okay.
see ocean, or line,
I think a harp looks
or
like
beach,
this, right?
or mouth, or knee. Oh, I know, it's
It's a harp.
harp.
Okay. Draw a bucket. All right. So a bucket should be.
I see canoe, or hockey puck, or cup, or paint can. I see mug. I see drum. Oh,
Then
I
you need the
know, it's
handle.
bucket.
Okay. And then the last one. So they give you six drawings. It's asking me to draw a duck here.
I see knee, or water slide, or foot, or shoe, or sock. I see swan, or snake.
Uh,
I see pigeon, or bird. Sorry, I couldn't guess it.
all right. So I got 4 out of 6, which is not bad. Um, and then if you wanted to click around, you can actually see the results from other people, right? So I was asked here to draw a jacket. And then I guess here is where um, the classifier thought our drawing looked closest to. So the correct match is a jacket. You can see that the other person here started off with the left. Second closest match, sweater, and somehow a camel, which I'm not too sure how they are similar, but I won't question it. And then you can see these are all the examples from other people, right? So this is something that, like I said, is just crowdsourced doodling. It's definitely very cool, kind of like social game. I was asked here to draw a duck, and I feel like one of the reasons could be maybe the way people drew like their duck facing left. Mine was right. So this one, yeah, maybe I could have drawn the beak a little bit better. Um, Clicking on this hyperlink here brings you to all of the different, the different objects that they've been doing, right? So for example, if I wanted to click into Apple, you can actually see just how many doodles there are, right? So it proudly shows all the drawings that were done. So if I hover over one of them or if I click on them, you can see it has a date and then the location, right? So very cool little game that Google made. And it clearly demonstrates how image classification works, right? Like we're drawing something in real time, and ultimately the classifier is trying to predict what we're drawing, right? So that's kind of just image classification in action. All right, now continuing on with the slides. My next thing here, I'd like to talk a little bit about the pros and cons of image classification, right? So let's start off with the good stuff first. So image classification can automate repetitive tasks like sorting images or detecting patterns, right? So that saves hours and hours of manual work when it comes to data sorting. Secondly, with the assumption that you're using high quality training data, it also has the potential to be super accurate, right? So you can kind of think of like real-time analysis in underwater drones or auto tagging species in research footage, right? And it's also very, very fast. So once it's trained, the model can run on phones, drones, and even in remote ocean sensors with very minimal processing power. Okay, so definitely some huge pros when it comes to using image classification, right? Automation, having good accuracy, and then also being able to make decisions in real time. So those are kind of the benefits. But then obviously, um, nothing is perfect. And with image classification, there's also some things we need to keep in mind, right? So first off, image classification needs a lot of labeled data to get started. Okay, so depending on your capacity, perhaps financial constraints, people aren't able to get all of the high quality training data with their associated labels. But if you don't have any labels, then your machine isn't going to be able to learn what it is that you want it to predict, right? Another point of concern would be bias. So if your training data lacks diversity, then the model might misclassify or perform poorly in real world use. Okay. Um, and the third and final point is with regards to interpretability. So um, understanding image classification, like the general idea of what it is, and also understanding its results um, is fairly straightforward, right? You're just taking an image and then you have a classifier trying to label that particular image with something. But it becomes much harder to fully understand why a model would get something wrong. Okay, we only really know like that, like we can confirm whether or not it's right or wrong, but sometimes it's hard to understand why our machine does what it does, why it thinks what it thinks. Um, so that's definitely one thing to keep in mind. It's the interpretability aspect of it. So as exciting as it is to jump into AI and computer vision, I think it's just as important to be aware of the risks that are associated with it. Right. So whether it's because you're relying too heavily on the confidence scores, or you are using a biased or incomplete training set, or perhaps assuming that the model will generalize well in new conditions, there's always going to be a little bit of room for error, right? Especially when it comes to um, reliance on machines. So you can think of your model when it comes to image classification. Think of it as like a very confident intern. Okay, so say you have a new hire that's an intern, uh, they will try their best to get the job done, but then obviously you will still need to provide some oversight for that new intern. Okay, that's probably the best way to think about it because one of the biggest risks, I think, is kind of like over trusting early results, and especially when you're working with sensitive marine data or environmental impacts, right? So that's why it's very important to first test your models in the wild, uh, continuously validate them, and then also incorporate human review where it's possible. So ultimately, AI should be assisting our judgment, but it should not entirely replace it. So now, when it comes to some of the data quality concerns, uh, ultimately, our model will only be as good as the images that we provided. So if our images has, for example, things like bad lighting or blurry shots or weird angles, that can throw off our model entirely. Okay. That would be like me trying to identify a fish through a foggy window, right? It's going to be much harder for me to do. So ultimately, if your input data isn't strong, then your predictions won't be either, right? So this is where we need to think about um, some of the aspects that could influence like poor image quality. Okay, so the first one is inadequate lighting, right? So you would have things like shadows or glare, low contrast. All of these things would make it tough for the model to detect the edges and patterns within your image. Um, like I said, it's like trying to identify a species when, you're in a murky underwater environment. It's going to be very hard for the classifier to do, right? So that's why it's important to first control the environment, control your lighting. So in some examples that we see here, first one being insufficient lighting, it's too dark, cast a shadow backlight. So this one here, the foreground is too dark because of the bright background. And then also this one here is underexposed, the final photo. Okay, so these are all kind of just uh, inadequate lighting examples. The next part is low resolution images. Okay, so our model, it requires enough visual detail to be able to detect those key features, those key patterns, right? If I have a blurry fish, then it could think that it's a rock, for example. So for especially high stake use cases like when dealing with endangered species tracking, you need those high resolution images. Otherwise, your accuracy will just be very poor. Okay. And then lastly, when it comes to image quality, we need to think about the angles and perspectives of our photos. So our prediction, our AM model will struggle a lot with unfamiliar perspectives if we only provide our uh, model with, images of a dog from the front view, right? So say like taking photos directly straightforward at the dog. Um, if we were to throw at our model a picture of our dog from a top angle, um, it wouldn't be able to classify very well because it's only seen the dog from a certain angle, from a certain side, and it might fail if I were to show it from um, an angle from up top, right? So the solution to this would be to train our model with a variety of different angles, okay? But not just different angles, but also backgrounds, different lighting. All of this can help our model generalize what a dog might look like instead of strictly memorizing based off of a certain strict subset of angles. Okay, so um, when it comes to dealing with unusual angles and perspectives, just always pass in a variety of different perspectives for our model. Now, the next point here is with regards to surveillance, right? So this is one of the biggest ethical flags that we have today, and it's definitely a huge topic that um, could go on for hours on end. But I'll just quickly kind of bring in a quick note for this presentation, right? So in our modern day, especially with the introduction of AI, you have things like image classification and how it's being used for facial recognition, behavior monitoring, etc. Right? So um, I'll just say that all of this data that's being collected, it opens the door to a lot of issues of consent and misuse and bias, right? So how um, you know, the specific details in terms of consent and misuse, those can be a conversation for a different day because that can, like I said, it's a huge topic that can go on for a long time. But essentially, with surveillance, we should ultimately agree that just because an AI can watch, right, and track doesn't mean that it should, right? So that's something to also keep in mind as we enter a new age in where AI plays a bigger and bigger role in our daily lives. So, um, related to surveillance, right, we have the topic of data privacy. So a lot of data sets, they can contain a lot of, um, identifying features, right? You have things like faces and license plates, for example, all of these things captured like from vehicles with a lot of camera technology embedded within them. Okay, so if these were used without consent, then it would cross a lot of legal and ethical lines. So whether or not it's, human beings or marine life or anything else, we have to think, are we first collecting this data responsibly? Okay, so that's also an aspect to keep in mind when we perform image classification. So all of tying all of that together, I think the phrase here is responsible implementation. Okay, in fields like medicine or in the criminal justice system, right? A bad or I guess like a um, mistaken classification can literally mean life or death. Okay, so the same idea would go for misidentifying species in conservation work as well, right? It's not just about like building tools, but ultimately we're using them to shape decisions. That's ultimately the end result of why we're creating all of these tools in the first place. Okay, so we need to advocate for fairness, transparency, and then making sure that the technology that we're creating does what it should, right? Not just what it can. So that's a key distinction there that we always need to keep in the back of our minds when we're using a lot of these modern day methodologies. So with that being said, I'd like to just bring up some examples in terms of when instances of where computer vision might have kind of not worked well. Okay, so there's definitely been some, uh, couple public controversies. Okay, so the two that I'm going to highlight here are discrimination cases and then self-autonomous vehicles. So for the first one, it's with regards to facial recognition. Okay, so facial recognition software has historically underperformed for people with darker skin tones, and this leads to misidentifications and real-world harm. Now, there's also the aspect of self-autonomous vehicles that are becoming more and more popular today. So you have some crashes that have been traced back to computer vision misclassifying objects, like for example, mistaking a white truck for open sky. Okay, so in the slides here, I have two links that I'll just quickly share. I won't go through, everything in detail, but we can just basically skim through the header to get an idea of the issues that were at play. Okay, so this one here is from MIT, and as you can see, the title says, Study Finds Gender and Skin Type Bias in Commercial AI Systems. Okay, so clearly something that's raising a red flag, that's something of a concern, right? And then the subheader says, Examination of facial analysis software shows error rate of 0.8% for light-skinned men 34.7% for dark-skinned women. So this is almost a difference of 34%, right? That is quite a substantial difference, right? That definitely raises you know, like some concern in terms of the lackluster performance for this facial analysis software, right? And this is just an example of some of the racial discrimination that can be at play when we build these AI tools. Now, I will say, this article, it came out like 7 years ago, so 2018. So by now, it's a fairly old article, and I imagine that a lot of the facial analysis, facial recognition tools that we use nowadays, um, the differences are very much minimized in this day and age by now. But I think it's still important to remember and be aware that this was the kind of challenge uh, we once faced as we were building these tools, because now we are able to remember that, okay, this is something that we encountered at one point. We need to um, acknowledge and be aware that we cannot have this repeat again, right? So for our own sake of learning and improvement, I think this is something important to highlight and just be aware of. Okay, so this was one kind of roadblock that we had. And like I said, I'm not going to go through the whole article. We can kind of get an idea of what it's saying through the subheaders. The other example I was talking about is uh, uh, our self-autonomous vehicles. Okay, so I have this article here. This article is from Bloomberg, and it's an article talking about a Tesla crash that shows the limits of full self-driving. Okay, so for those who don't know, Tesla, right? The EVs, they have autopilot, but then they also have full self-driving. So for those who don't know, the difference between the two is that autopilot is kind of like, it's kind of like the more basic kind of driving assist system. Full self-driving builds on top of what autopilot offers. So autopilot, it's kind of like able to, if you're highway driving, it's able to help control your speed and maintain within the lanes. Full self-driving takes that one step a notch by, literally being able to like brake and accelerate and turn, all of those things. Okay, so it's kind of just like autopilot, but even more autonomous for the vehicle. Okay. So just skimming through this article here, okay, basically the situation was that the sun was setting and then it was blinding not only drivers but also the camera system that you will see later in these couple clips. Okay, so this one is fairly new. Okay, so 2025, I think. But the crash itself happened in 2023. The article came out in 2025. Okay, so you just have this person named Jonah and her daughter. They were driving a Toyota 4Runner. Okay, and then uh, we have this Tesla. Okay, so Carl Stock. Carl was driving a Tesla, and then Carl was using FSD, right? FSD, in which Elon had stated that just 18 months earlier was high stakes. Okay, it was a high stakes work in progress, right? That's something to keep in mind. So basically, Carl's Tesla hit Jonah. Okay, the she's a 71-year-old grandmother at highway speed, and then she died. Okay, so clearly something very serious. So let's take a look at what happened here. Okay, so this is footage from a front camera on Carl's Tesla. And as you can see, it's making, it's just driving towards the left, slight bend, and then you can see the sun come into view, right? Sun glare becomes more pronounced around the curve. And then as it's driving, you can see that a car on the right lane begins to brake, but the Tesla still appears to maintain its speed. Okay, so clearly, like on the highway, there seems to be some kind of stop going on, right? A lot of cars, most cars are all stopped, but the Tesla isn't showing signs of slowing down. Okay, so definitely a little bit concerning at this point. More vehicles with hazard lights are parked on the right shoulder. So more and more vehicles, right, on the right-hand side, you can see are stationary, but the Tesla still hasn't braked as they come into view. So it seems to be still driving at highway speed. Okay, so at this point, it's getting very dangerous. So now you can see a person waving to get the Tesla driver's attention. Okay, so at this point now, I think based off of the sudden kind of like movement of the vehicle, of the camera, I think Carl grabbed a hold of the wheel and realized what was going on. Okay, so now it's frantically trying to slow down. And then you can see that it's not braking in time. And then the Tesla sideswipes the Forerunner and then hits Jonah head on. Okay, so um, yeah, that's the collision there. Okay, so clearly this was like a very unfortunate right tragedy that occurred that one can say could have easily been avoided. Perhaps if like the car was driven by a human instead of relying on full self-driving. Okay, so that is also one of the more, I guess, like damaging and unfortunate situations, instances that computer vision has definitely fell flat on its face for, right? And the reason for this is essentially just with regards to glare, right? So the reason why all of this happened in the first place was because of not just the time of day in which the sun was setting, but also the fact that um, Carl's Tesla was driving directly towards the sunlight, right? So then the sun, it was essentially blinding the cameras on the Tesla, and like it wasn't able to detect anything else in view. Okay, so um, definitely, while computer vision is helpful and it's doing a lot for humanity, we also need to just keep in mind of the limitations that are going on. Okay, so those were the two examples that I wanted to share. So next up, I wanted to look a bit into how image classification can be used within the ocean sector. So the first example that I wanted to talk about is a company called Smart Catch. So this company integrates high definition underwater cameras. They call their cameras DigiCatch, and they place them directly into these fishing nets. So now fishers are able to see in real time what is going on in their trawl nets. Um, Basically what they're looking for are the right species to catch. And if it's not the right species in their net, the system allows the fishers to release them right away. And so this ultimately prevents bycatch. That's kind of what they're trying to go for here. Okay. Um, by being able to prevent bycatch in their nets, it's a huge benefit, right, in terms of biological diversity, in terms of sustainability. And also, for companies themselves, they also have a financial incentive to make sure that they know what they're catching, because if they like mistakenly catch an endangered species and they don't release it, they could face financial penalties, right? So not only is it for biological diversity, but also from a company financial side as well. Smart Catch, they also do a little bit of work in terms of image enhancement. So, you have cameras underwater, and a lot of the times, it's like those murky deep sea environments where, like, it might be a lot of dirt, a lot of mud, maybe like the water's like murky, it's not clear. So, Smart Catch also, they do a little bit of work in image enhancement. Okay, so this is all technology that ultimately helps fishers make fast and ethical decisions. So as you can see here, on the top left corner, that's the high definition camera. So they call it the DigiCatch. And then on the bottom right, you can see some fishers putting that camera into a net. Okay. And so they basically, have the trawl net around in the water. And then they can see through that camera what kind of species they're catching. Within that camera, they have a classifier model that is able to help them detect and classify what species they have in their net. And if it's an endangered species, they just let it go instead of traditionally, right? I'm sure the fishers they do their thing with their net. They bring it up, and then they would probably need to like manually sort through the fish, right? So that saves them a lot of time. Instead of having to bring it all the way up while they're still in the water, they can just let the fish go. The next company is Ocean Diagnostics. Okay, so these folks, they tackle microplastics. Okay, that's what they specialize in. And they try to analyze microplastics, whether or not they're found like in ocean waters or in animals as well. So Ocean Diagnostics, they developed something called the Saturna. So this Saturna is essentially kind of like this high quality definition camera that uses computer vision to classify plastic particles, whether or not like it's foam or pellets or film. Okay. And the Saturna, they have 13 distinct metrics to help them kind of like automate the measurements that they take. So they always look at the max width of like this microplastic, circularity, etc. And they also have a standardized setup environment. So they always have like this bright ring of like LED lighting along with a backdrop, right? So this ensures uniformity in terms of the imaging conditions in which you uh, analyze your microplastics. So here's a Certana here. It's just like a big bright ring with a HD camera. And then you have the black backgrounds, perhaps for the brighter plastics. And then you have a white background for the darker ones. And then next up, I have Flukebook. Okay, so Flukebook is a company that specializes in whale identification. So each whale's tail, or fluke, which you can see in the bottom right, this is what a fluke looks like. It is uniquely patterned, right? So, it can have unique markings, separated left and right. The shape of the leading edge and trailing edge could also be different, right? So these are all unique identifiers that uh, a whale could have, right? It's through the tail. So Flukebook utilizes image classification to match newly taken photos of whales to individuals in a massive database. So it can kind of keep track of where the whales are, right, location-wise. And so far they've taken like I think around 86,000 whales so far, right? 86,000 um, logged. Okay, so quite a big database in terms of whale conservation. And this is a huge plus because it can help speed up perhaps what used to take hours of human effort, like manually scanning through photos, into just like mere minutes, right? So it's a game changer for whale conservation work. Okay, so through here you can kind of get an idea of the points in which it looks to uh, converge on as it tries to focus to uniquely identify what whale it is, right? So along the trailing edge here, right, there's a very distinct line and pattern going on here. And then it looks at other specific pinpoints in terms of shape, I imagine, right? So all sorts of different types of marks that can identify and indicate each individual whale, and they match it with their database that they have. Okay. Um, so yeah, next up is something called Teachable Machine. If you guys remember earlier today in the presentation, I said we were going to do a hands-on, free, low-code online tool. So that's what we're going to do now. It's called Teachable Machine. So what is it, right? Teachable Machine is a web-based tool developed by Google Creative Labs, and they do classification on a variety of different data like images, sounds, and poses. It is fast, free, and very simple to use. Okay, so uh, let's go ahead and get started here. So I just start off by typing teachable machine, and then I can also just paste this link into the chat so it's easier for you guys. Okay, here you go. So go ahead and click on that link that I posted in the chat. And then basically I'll just do a quick rundown of the website here. So it says train a computer to recognize your own images, sounds, and poses. Okay. Create ML models for your sites, apps, and more. No expertise or coding required. Okay, it's a very low-code tool. Very simple to use, straightforward. Anyone can use it. And then I'll go through a quick demo today as well. So I'll just play this video actually, so we can know what's going on.
People are training computers and creating machine learning models to explore all kinds of new ideas. New ways to interact.
Yes.
To understand the world, to play, and experiment. But machine learning is pretty intimidating to get into. So we've been wondering, what if it wasn't? With Teachable Machine, we set out to make it easier for anyone to create machine learning models without needing to write any machine learning code. When it first launched in 2017, it allowed everyone to get a feeling for what machine learning is all about. But now, Teachable Machine puts the power of machine learning in your hands, allowing you to save your models and use them in your own projects.
So let's say you want to build a model to recognize you versus your dog. You just open up the site, record samples of you and samples of your dog. Click Train, and you instantly have your own machine learning model, which you can use in your sites, apps, and more. You can upload your model to host it online, or download it to work entirely on device.
With Teachable Machine, you can create custom models for all sorts of things. Using images, audio, or even poses. Personalized machine learning models for the things that matter to you. And folks have already been trying it out, using Teachable Machine in their own experiments, solving problems in their communities, or even just at home. Start creating and see where your ideas take you at g.co/teachable machine.
Okay, awesome. So, they also provide instructions on how to use it. It's a very simple three-step process. The first step, of course, is to gather your data. So, you know, upload or take photos of examples of your classes and then categorize them, right? Second step, train your model. It's as easy as clicking a button. Third step is to export your model. So you can export it out to sites or apps or more. You can share it with other people. You can download your model, and you can also even host it online too, right? So what can you use Teachable Machine for? Well, it's very flexible in the sense that you can use files or you can capture examples live in real time. Um, it's respectful of the way you work. Choose to use it entirely on device without any webcam or microphone data leaving your computer. So that idea of data privacy is also something very important and something that they always kept in the back of their minds when designing a tool like this. You can use Teachable Machine for your images, right? So classifying images using uploaded files or through a webcam. You can use sounds to classify audios by recording short sound samples and also pose estimation, which we talked about earlier. So you can teach a model to classify body positions, right? That's also something that's very interesting, whether or not I'm standing or squatting. So I just wanted to quickly take a look here just to showcase one of the examples that are being used. This thing's called Tiny Sorter. Basically, uh, it is a DIY experiment in which all it really is, it basically sorts whether or not something is cereal or marshmallow. Okay, so very simple, very straightforward, easy to use, but you can see it in action, how it utilizes that computer's webcam to tell whether or not it's a cereal or marshmallow. Okay, so all sorts of different neat little things that are being made using this tool. Okay, so now that we kind of have an idea of what we're going to work with, let me show you the data set that we're going to be using today. Okay, so I'm going to paste into the chat here. It's a link to Kaggle. So Kaggle is kind of um, like a repository hub for a lot of data scientists for them to do their work. And then here I have a data set on uh, marine marine imaging. Okay, so this is a benchmark data set to classify dolphins, fish, lobsters, octopus, and seahorse. Okay, so it sounds very relevant to basically what we're going to do. Just quickly skimming through the about section here. It was, this data set was used for a research paper, comparative analysis of ML algorithms for marine animal detection. So it sounds very relevant and closely related to what we're doing today, right? What it what it was used for is to evaluate and compare the performance of various ML algorithms. Okay, so that's very cool. Um, Taking a look at the data set itself, you can see that there are 5 categories which were listed up above here. Okay. And then for the training data, they have over 1,000 images, validation data 250, test data 100. Their format is RGB. Okay, their purpose to benchmark these different uh, models and algorithms that they're trying to test, basically to compare performance, and they use these marine images as a benchmark for it. Okay, so I'm going to download this data. So you can just click on the download button here, download as a zip folder. So just wait for that to finish. All right, so the download here is complete. I just have it here in my file explorer. It comes through as a zip file, so you need to first extract it. Okay, so I click extract all there after clicking the zip folder. And then, like Kaggle said, right, it had like over 1,000 images. So it's definitely a good data set, right? Because like I mentioned in the slides before, the higher quality our training data, the better our classifier is able to um, tell uh, our data. Being asked to sign in. Okay, so I see your question there. If you don't want to sign in, don't worry. I also uploaded all of these images onto a Google Drive repository. So if you don't want to create a Kaggle account, you don't have to. Um, I'm just showing you the source of where like I got my data, right? It was from Kaggle, and then they used it for this research paper here. I think the credits are like somewhere down here as well. Yeah, I will show you the Google Drive link in a couple minutes. So yeah, just hang on tight. Um, so okay, so I've unzipped the folder here, going into these different layers. Okay, so at this point here, we have three separate folders, right? So they mentioned that the training data, right, 1,200 images, validation 250, and test data 100. Okay, so um, basically, for those who don't know, right, for training, validation, and test data, um, for our use case today, we're only going to use the training data and then the testing data. The photos in the validation folder, we are going to ignore, okay? So validation data is basically used when you need to basically compare the performance when adjusting for trying to figure out the ideal hyperparameters, okay? So hyperparameters are basically the settings of your machine learning model, right? You can kind of use it to fine tune the performance, the accuracy to improve it, right? There may be sliders that you want to adjust. But in our case today, when we use teachable machine, for the most part, the default configuration of the machine learning model that they provide to us will be enough. So we do not need images from the validation folder to try and figure out what the ideal configuration is, if that makes sense. Okay, so let's just ignore the validation folder for now, and then look at the training and then the testing folders. Okay, so going into the training folder, let's take a look at what we have. Okay, so we have seahorse, octopus, lobster, fish, dolphin. Okay, so looking at this training folder, right? Like I'm curious, 1,000 images, what's the size of that? We're looking at around 82 megabytes worth of image data. Okay, so definitely a sufficient amount of sample image data to pass into our classifier. That's definitely something you should always check first to see whether or not it's a sufficient amount of data that you have. The next step is to actually go into the folder to see what images you actually contain, right? So are there like different angles of dolphins being taken, for example, right? That thing that we were talking about before. So going into these folders here, I'm able to change my view to be able to see the dolphins a little bit better here. Okay, so as you can see, the dolphin folder, right, seems to have a pretty good diverse, collection. We have some that are above water, some that are underwater. We have some facing different directions. I think there's a couple that are like facing the front, like this one, for example. Okay, so yeah, the diversity in terms of angles, right? The lighting seems to be okay. Um, and then just quickly going over also the file types, right? So for example, within the lobster folder, I'm able to filter by type. So you can see we have JPEG files, we have PNG files, we have something called a WebP file. Okay, so also consider the file types that are being provided in our image data set here. Okay, so octopus is JPEG, right? Seahorse, okay, all of these. And then maybe also just checking to see how many photos there are in each class, right? Going back to what we were talking about in terms of like bias, right? So how can bias become a problem in our model? Well, the situation could be that maybe we have a lot of examples that are seahorse and octopus, but then like lobster might only contain 10 images, for example. So that is what causes bias. It's when there is an overwhelming majority or there is not enough representation across all of our classes that we're trying to predict. Okay, so that's also something important to check. So, okay, seahorse has 250, octopus, it's got like 250. Um, I won't check every single one, but I can assure you that most of them, they have like similar amounts. And then I think dolphin is the least. This one might only have like 200, right? But it's not a drastic difference enough to the point where we need to worry about introducing bias in our model. Okay, so these are all the images that we downloaded here, right? Seems to be a good quality. Um, so dolphin seems less, but assume it needs less to train due to its shape. So yeah, that's also a good point there, John. With um, the variety, right? We also need to think about the diversity of the species itself. So, with dolphin, when we think of a dolphin, like I think it's a general consensus what it might be, right? Like it's gray and then it has fins, it looks a certain way, right? We all know what a dolphin looks like. But then if I asked you to visualize a fish, right? That could have a bit more variety. Okay, so for example, um, if I look into fish, right, you can see that there's like all sorts of different types of fish. Okay, so um, I don't have a marine background, so I can't tell you like the species of all of these, but like some are like orange and then some are yellow, right? So there can also be different types of fish as well. Okay, so that's also something to keep in mind. Same idea with like cats and dogs, for example, right? Like dogs, there can be so many different breeds, but then for cats, right, it's more or less all the same. Okay, so that's also something to keep in mind. So this is where, like I said, right, you have the idea of like that very confident intern. You still need oversight, right? You still need human intervention. So in a case like fish, it is up to you to decide whether or not it is necessary to break the fish down into further categories, right? Um, like you can have like goldfish or like, whatever the case may be. But, each folder, it's got around 200 images. It's more than plenty for our purposes today. Okay, so now basically what I did was I took the training and the testing folder and then I uploaded it onto a Google Drive dataset. Okay, so let me just plug the link that into the chat right here. So that way, for those who don't want to create an account on Kaggle, you can access the images this way. Okay, so opening up that folder, right, you can see I have a training and then I have a test. I basically just took what I have here and then brought it over into here. Okay. So now that I have all of this data, we can go ahead and jump into Teachable Machine. Okay. So I'm going to click on Get Started. And so with a new project, first I have two options. If I already have an existing Teachable Machine file, I can either open that existing file if I downloaded it locally, or if I uploaded my Teachable Machine file onto Google Drive, I can also open it from there. I'm going to create a new one from scratch, and then as we talked about before, you can pick between image, audio, and pose, right? So we're gonna do image here. Okay. Between the standard and the embedded, pick the standard. So embedded is used like for more smaller scale, devices with a bit of like, I guess, computational restraint. Here we're using 224 by 224 pixel images. Okay. Color images as well. This one only does grayscale. Oops. Okay, so image project standard. Okay, so this is the interface, right? As you can see, very, minimal, um, like not much going on. Okay, so the first step that we need to do is assign our labels. So if you recall, we have 5 categories, okay? So I'm just basically going to list out all 5 of these categories right now, right? So for the first class, we have dolphin, right? For the second class, we have fish, right? For the third class, lobster. The fourth one, uh, octopus, and then finally seahorse. Okay, cool. Um, So now that we have our classes, um, you have the choice between webcam. So this is kind of like the live feature, or you can upload images, right? So if I click on upload, I have another 2 options. I can either upload files that were downloaded locally on my computer, or I can upload them from Google Drive. So I'm going to show the Google Drive method because when thinking from a practical perspective, right, from a day-to-day like workplace environment, people don't send like, giant files to each other, I don't think, right? We use kind of like a shared workspace like Google Drive, where perhaps someone from the Pacific is uploading images of dolphins that they took, right? And then someone from the Atlantic is, I don't know, uploading pictures of octopus that they took, just as a use case example. Okay, so I'm going to upload images from Google Drive. I'm going to sign my into my account here. And so I am precisely going to look for this marine species folder here. Okay, so after signing in, you can see I've got my marine species folder, right? So then from here, we're going to begin to upload the images that we use to train our image classifier. So uh, right? Between the train and the test, right? So which one do we use? So the training data, as the name suggests, is going to be used to train our model. So these are the images that our model will see to learn the patterns, right? Like the edges, the lines of what a dolphin might look like, of what an octopus might look like, okay? And then after these training images are shown to the model, we don't want to show those same images again because in a sense, our model has kind of already seen certain images of what a dolphin might look like. So that is where the test folder comes in. The test folder contains images that were not shown to our model yet, right? So then, in a sense, it's kind of like a new question. Like we are testing our model to see, okay, do you know what a dolphin looks like? If I showed you this photo, are you able to tell me with accuracy that it is a dolphin? Okay, so that's kind of the difference there. So in our case here, we need to use photos only from the training folder. Okay, not from the test, from the training folder. Okay, so okay, yeah. So I'm going to train, and then this one is dolphin, right? Now the way Teachable Machine works is, um, like you kind of need to scroll down a lot. Um, and maybe I'll show you what I mean in the next one. But basically, only after that you scroll until the bottom can you Control A. I hold Control, hit A, press select, and then it would upload all of the dolphin images. Okay. So just give this a moment. It'll upload. It might take like a second or two. So just be patient. Okay. Okay, cool. So this one, yeah, 198 dolphin samples. Great. For fish, I will kind of show you what I mean. Um, with like this little like I guess like quirk that Teachable Machine has. So with fish, right, as we saw in the training folder, it should have around 288 photos. Okay, so quite a lot for fish. Um, like if I was new to Teachable Machine and then I open the fish folder and then I just hit Control A right now and then I try to upload everything, you'll see that it doesn't upload all 288 images. Um, so we'll see how many images it actually uploads here. So like I said, just yeah, just give it a moment here. Right? So okay, that's weird. It only uploaded 50. Okay, so that's definitely not right. We should have 288. So let me just do it again here. So I go into marine species, right? It's the training data, and then I go into fish. So it's just one of those like things that you only really figure out until like you actually use the product. So if I'm like new to Teachable Machine, say I'm a new member on the team, and then I assume that everything works, I hit Control A. No, that's not the case. This one's a little bit tedious in the sense that you need to scroll all the way down to the bottom until there's nothing more that can be loaded. That's when you hit Control A and then you upload. Okay, so just kind of like a small quirk there, but just like keep that in mind. Yeah, it's definitely a little bit annoying, especially if you're a new user. You would assume that Control A can capture everything, right? And then you do that, and then you think, oh, like my team only took 50 pictures, right? But that's not the case. You took like over 200. And then, it leads to incomplete data, and then your model won't perform as good as it does. So that's why I said earlier before, um, it all starts with your training data, right? The more data you feed to your model, but obviously it needs to be good data because if it's like poor quality data, it can also misconstrue our model into thinking what a dolphin shouldn't look like as well, right? So not just quantity, but also quality. And as long as we have good training data, then our model can perform the best possible. Okay. So for lobster, let's just do the same process here, okay? So just do the same thing here. Marine species, train, lobster. So uh, one quick thing I will note for Teachable Machine, and so just so you guys are aware, okay? So if I go into lobster, right, and then I go into the categories, you can see that I have one called a WebP file, okay? It's called American dash lobster. And then I'll just let you guys know right off the bat, Teachable Machine only accepts like JPEG, so both JPG and the one with E, as well as PNG files, as far as I know. Okay, so if I actually try to search for this specific type image, um, I won't actually be able to find it. Okay, so if I took the name here, right, and then I tried to look for it, in my lobster folder, you can see that it wasn't found. Okay, so that's just one thing to keep in mind. Not all kind of like image types are supported in Teachable Machine. It's mainly like JPEG and then JPEG with the E as well as PNG files. So those are the ones that work. Okay, so I'm going to take all the lobster data and then we just give it a moment to upload here. And then I think like WebP, it's kind of like Uh, it's kind of like an image file type that's like based in a web browser, I think. It's not like a traditional image, um, if that makes sense. Um, so yeah, right. So you can see that not all 252 images were uploaded two are missing. So one of them is the WebP file, and I'm actually not too sure what the other one is actually, because we only have one WebP file. Uh, so there's another one that's missing that I was not able to find out, but for the most part, pretty much it's just JPEG and uh yeah, PNG. And then I'll just do one for Octopus here. Okay. So the same kind of thing where you just need to kind of be a little bit patient if you have a lot of photos. Gotta just like go all the way down to the bottom here. Okay. And then just give that a moment to come through. All right, Octopus. So that one's done. And then for the final one here, I want to do something different. So instead of uploading images as we've always done before, what I'm going to do is try the webcam function. Okay, see how that works. So for the webcam, I think the reason why it's not working is because I have my camera on Zoom. So I'm just going to turn off my camera on Zoom, and then now I think it should work. Okay. Okay, cool. Yeah, so yeah, there's me, and then you can see, right, I have if you have different webcams, toggle that one, crop. So um if you didn't notice, right, all of these images that we provided are in a square, right, format, even if the original image was rectangular, right? So if you remember, we had that 224 by 224 pixels, right? The nature in which CNNs work, it's also square, because of the filters that they run over. But basically, like the images, it's going to be square, right? So even though my laptop, right, it's in a rectangular screen format, it crops the image into a square. And then if I want to flip it, I can. So this just mirrors the image. Some settings here in terms of the frequency in which you capture the image. Okay, so let's see what happens. How does this work? I hold to record, right? So you can see it just captures images of me at a specific frame rate, and then we'll go like, I don't know, 150 images. Okay, so 150 samples is basically just selfies of me. Okay, so for now, let's pretend this is what a seahorse looks like, okay? Images of this is what a seahorse looks like, right? And then we uh, just train our model with a click of a button. Okay, so very easy to use. So just give that a couple seconds for it to train. And then we can begin to throw test images um, our at our model. Okay, so if this pops up, just click wait. Okay, so our model has been trained. And we can see that this is the area that we go to basically begin testing our model, right? So everything that we've done so far is trying to teach our model, okay, look, this is what a dolphin looks like. This is what a fish looks like. This is what a seahorse looks like. And now we're able to test it. So right now we're testing our model through the live webcam feed. So right now it's 100% seahorse, which makes sense because that's the images that we use to denote what a seahorse looks like. At least that's what we told our model. Now, if I didn't want to use a webcam and I wanted to use file, well, I have the option for that. Once I select file, I can pick between locally downloaded versus Google Drive. Okay, so let's just take some from Google Drive here. And then now remember, right? Instead of the training folder, now we need to go into the testing folder because our model has already seen pictures from the training folder. So it's going to know, like, it's going to know that this image here is of a lobster. There's no point in asking that, right? So we need to go into oh, marine species, right? Marine species, and then we go into test. And so this is where you can just basically play around with whatever and just try a bunch of different images. Okay, so with 100% confidence, our model thinks it's a dolphin. Solid. Yeah, I would agree. Um, right, you have one like octopus, for example. Right. Okay. Solid. Okay, so 100% octopus. That looks good. But now, let's try something different here. Okay. What? Let's think about what would happen if I uploaded an actual picture of a seahorse. Like if I went into my testing folder, right, and then I picked like any picture of like a seahorse, like this seahorse, for example, right? That would definitely be a curveball for our model because the images that I told my model what a seahorse looks like are pictures of me. Okay, so now I'm actually going to give it a picture of a seahorse. I'm really curious to see what our model predicts it to be. Okay, so let's see. Um, we go here again. Okay, so with 100% confidence, our model thinks that this image is an octopus, right? So from uh from like from like a human, right, point of view, we know this is wrong, right? This is clearly not an octopus, but then our model with 100% like probability, right, thinks that it is an octopus. So going back to, what we've been talking about before, treating things like this as an intern, okay? You still need human oversight. You still need someone to kind of manually verify to check, does that really make sense? Is that reliable? Is that correct? That kind of thing, right? And one of the, I guess, like, I think one of the quirks, not just with teachable machine, but with AI as a whole, is the assumption that the AI like is always going to try to give you like a full answer. So so one of the flaws of teachable machine is that it always needs its 100% to be achieved somewhere. Whether or not it was, for this example, maybe it could have been 50% octopus, 50% lobster, right? It is never the case where you can see all categories having zero. Okay. So um, that's kind of a major flaw with teachable machine, I think. Um, if if you don't like give each of your classes the right training data and from a human can verify that it makes sense, teachable machine is forced to always make a prediction that sums up to 100%. It does not know when to say no, basically. Um, so I think that's one of the issues with AI nowadays. I think it's that a lot of times AI is like it doesn't know when to say no. It always tries to give you an answer, but that answer might not be correct. But to them, they don't the AI doesn't know when to actually just back out of a conversation and just identify this is completely wrong. Okay. Um, how about trying a different picture that was not used to train the model? Yeah, so that's exactly what I'm doing here, right? I'm using a different picture that wasn't used anywhere in the training data, right? So I'm using a picture of a seahorse, but in my seahorse class, it's just pictures of me. And so this is where we can see where something can go wrong, right? And if I'm like a very naive like person who just blindly trusts what the output is, I see, oh, like it's 100% octopus. It has to be right. That's not always the case, right? That's not always the case. So that's something we need to remember to keep in mind. Um, So I'm just going to try the webcam version again. So it's with 100% seahorse, right? So that makes sense here. Um, and then like with the webcam, you can do all sorts of things. Like what happens if I were to like, you know, hold my phone? You see that? So it's very like like you can change a lot when it comes to a live webcam. So it's just very interesting to play around and see how like, oh, like why is that? Like if I hold my phone into it, it somehow thinks it's an octopus, right? So that idea of like human checking again is very important. Um, so yeah, so now I think we can do it the proper way this time. Uh, with regards to like these three dots on each class, I'll just quickly go over them. You can delete it entirely. If I wanted to delete Seahorse, or I can disable it. So now if I were to train my model again, it would only be these four. So disable is good if I need to come back to it and enable it again. Delete is you remove it permanently, which not everyone may want. Okay, so what I would want to do here is remove all samples. So I'll do that. You can also download the samples that you have, and you can also save them onto Google Drive. So lots of options for you to use. Okay, so I'm going to remove my samples, and then now I'm going to properly tell my model what an actual seahorse looks like. Okay, so yeah, just give it a moment. Um, okay, so with our seahorse, yeah, we've got around 250 images. Okay, so that's pretty solid. Um, so since we changed our training data, right? We changed the image data for our seahorse class. We need to we need to train our model again. Okay, so uh, yeah, that's something very tedious, but that's just something that we need to do. If I were to, for example, if I found another picture online of a seahorse that I really like, and I just wanted to add one more on top of the 252 already existing seahorse images, I would need to retrain that model again, even if I just added only one image. So that's something that there's no workaround, you know, it's just that's what you need to do to use it. So we're just going to train our model again here. So just give it a moment. Okay. So now we have it defaults to using a webcam, but what we want to do is test with our file. Okay, so let's upload an image here. So I think right now it might be bugged. We might need to upload a fresh image for it to properly verify. Um, so like we can try Dolphin to start off with, but most likely Dolphin will be very good. Hmm? Test Dolphin. Right? So 100% dolphin. Okay, that's great. Just play around with a couple, like with a handful, just to get an idea of like how well it's doing. Like for example, octopus, right? Like maybe I wanted this photo. Okay, 100% octopus, right? So that looks good. test. And then which one haven't we done? Like, we can try fish. Okay, so you can see that it's not always perfect, right? This one here um, thinks with 99% confidence that it's a seahorse. Okay. And we already have like our complete model here. It's not like I'm using the wrong photos, right? Like these are seahorses, these are octopus, these are fish, but this one here, it's a seahorse, right? So now we have like an ideal model that's going on here because we kind of set everything up correctly, at least in our mind, but we're still getting something wrong. And so if you remember, I talked about one of the downsides of image classification being how it's hard to interpret, right? So from our end, we think our model is set up perfectly. We did everything that we could, essentially, but it's still giving 99% seahorse, right? Do we know why? Not exactly, right? But if we could come up with guesses, right? So if I had to guess, like maybe it's because like the fish is like yellow, right? And then a lot of the seahorse examples that we gave are like, they have like some yellow seahorse maybe, right? But at the end of the day, we're not entirely sure. So that's one of the downsides, like I said, right? It's hard to interpret, it's hard to understand why it's wrong. We can clearly see that it's wrong. That's not the concern, right? The concern is understanding why it's predicting 99% seahorse. We don't fully know. Okay. Um, but we can make our guesses. So one of them could be color because a lot of other fish is uh, you know, of the Nemo type. Um, how could we fix this problem? Well, maybe if we introduced a bit more, yellow categories of fish in our fish training images, then maybe this would have been a little bit better. But if I recall, the vast majority of fish images that we gave our model, they look like Nemo, right? They're like the orange kind. They're not the yellow. They're the orange. So that's probably why we have a little bit of imbalance in our fish training data set. Okay. Let me just try one more here. Let me try the seahorse example. So maybe even the same seahorse image that was initially predicted as a dolphin, and I just want to see whether it still thinks that. Okay, so as you can see now, it's 100% seahorse. So initially it was just a little bit bugged. Okay. So yeah, there's that's how we can, use the file upload aspect. I'm just gonna switch back to webcam because now I'm curious. Um, if if our model, like if my model saw a live cam feed of me in which I hopefully look nothing alike to what was provided here, I'm curious what the model would think I look like. Okay. So, oops. So if I were to switch to webcam, okay, so it thinks I'm like majority seahorse, okay? And you can see that it's also very unstable. So even if I just move my head a little bit around, right, you can see that the probabilities are drastically fluctuating. Uh, and the reason for that is simply because this machine, like our model, has no idea what it's looking at. Because across all five categories that I provided my model, none of which contain pictures of me. So, so my model right now has no idea what it's looking at, but because it's programmed to be forced to give an answer that sums up to 100%, it's drastically fluctuating its probabilities across each class, right? It's highly unstable because it's looking at an image that just has no sort of resemblance to what it's seen before, to what it was trained with, right? So that's why the numbers, are drastically jumping up and down, and they're just very unstable. Okay, so um, that's why yeah, that's what happens. Um, so yeah, that's basically a teachable machine. Last couple of things I want to demonstrate here. So you can also export your model as a link. Okay, so if I go to export model and then I click on upload, okay, um, you can see that it created a link for me right here, right? So I can take that link and then let's say I opened a new private browser, okay, incognito. So this can mean anyone around the world can go onto this link and they'll see this. Oh, okay, interesting. So um, it seems like, I'm not able to, I don't have this left-hand side anymore, right? I All I could only do is kind of like upload files and access my webcam feed. Instead, on the left-hand side, it gives you like instructions. Okay, so say I send this link to like one of my friends who doesn't know what Teachable Machine is. Okay, so it tells me what it does, like how it works, all of that good stuff, right? So this is good because if I were to send this link to someone, I don't want them to change my data, right? Nor do I want them to have access to the uh, data that I train my model with, right? So, that's how it was designed. Anyone around the world, any stranger can use my model, but they can't modify my model. They can't access nor change the original training data that I originally gave it. Okay, so that's kind of the key there. Um, so if I were to upload a file, right? uh, I would first, from a human perspective, check that my image is of either a dolphin, fish, lobster, octopus, seahorse, whatever. That's the first check, right? That's where the human intervention comes in. So if I know, like, my image is of these categories, I can kind of verify it, right? So uh, since I'm in private, if I need to do this, I need to log in. So now let's maybe just try the upload option. So I go into my marine folder and then I go into test and then I go into dolphin, 100% dolphin. Great. Let's just try a different one here for good measure. So for example, if I wanted to maybe try fish, right? A fish might be a bit trickier because fish can look like so many different types, right? So this one here, as you can see, it's also not performing that well, right? 99% probability that's an octopus. We know that's wrong, right? But in the real world scenario, we won't necessarily know the answer to that. It's only until we train our model rigorously to the point where we are confident enough that it is able to predict the correct answer every single time, right? Um, so this one here, it also thinks like it's an octopus. This one's blue, right? So I feel like maybe it's the color thing that's throwing it off, right? Ultimately, we're not too sure. We don't really know. So if I just went to large icons here, I picked this one. Okay, so see, this one is a fish now, right? Which is good because in our training data, we used a lot of Nemos, not a lot of yellowfish and not a lot of bluefish. Okay, and I think the data set was specifically designed this way to kind of test for things such as that. There are easier classes and there are harder classes. Okay, so that is the export option. And then I can also like save my project to Google Drive, or I can download this project as a file. So both of these are pretty similar. I think I'll just demonstrate the offline download for now. So if I wanted to download my project as a file, okay, so let's see what happens. Okay. Um, so as you can see, the file that was downloaded is project.tm. Okay, so .tm, that is a proprietary teachable machine file type, right? That's only specific and it's specialized to teachable machine, no one else. Okay, so um, and let's pay attention to the file size of this, right? It's only 23 megabytes or so. So within this 23 megabytes, it contained basically all of my training data. Okay, so let me just show you how this could work. So let's say I wanted to open a new project. And so this is where those two options come into play, right? I can I can open an existing project from Google Drive. So that means if I were to upload this project.tm file onto my drive, I'm able to do that. Or I can open it locally. Okay, so I'm going to showcase the second option and then use project.tm, hit enter, and let's see what happens. So it's loading my project here. Okay, so as you can see, um, just within those 23 megabytes, it was able to capture over 1,200 images, right? Why is it able to do that? Well, mainly because the file dimensions are so small, right? So it's a small 224 by 224 pixel image. It's very compact. That's why it's able to cram all of those images into a very small file size. Okay, so this form of sharing is different from what I just showed you in the private browser. The private browser is for any stranger, right? Anyone that you want to be able to use your model. But in this case here, right, this project.tm file, it exposed all of your training images. So this might be good if you were to send this to like a colleague of yours, like a coworker at your company where, maybe your coworker needs to work on a different species or something. They're able to take what I have here and build on top of it, and then and then my coworker can pass that back to me as a form of .tm file. Okay, so those are the different ways of file sharing. Okay, so yeah, that's basically a teachable machine. The one last thing I want to highlight about it is if you open the menu, there's also an FAQ. So this FAQ here, right, what is it, all those things. But then perhaps the part that people are interested in uh, is with regards to privacy, right? So for example, who can access my files? Okay. So Google says your samples aren't sent to any servers unless you save your project onto Google Drive. But even then, it's password protected, right? To access your Google Drive, it's protected by your authentication. When you train the model, it trains in your browser tab without sending anything to any servers. Okay. The other question, where is my model published when I click upload? So uh, your model is published to Google servers, right? However, the examples that you used to make the model are not. Just your model, the mathematical program that predicts which class you're showing it, right? So if you recall that incognito browser, Teachable Machine generated a URL. Any stranger can go into that URL, but what they were basically able to only access was the mathematical program that our model implemented when being trained upon from our image data, right? Because if you recall on the left-hand side, they were not showing the actual images that were used. So that's basically what they mean by this sentence here. Okay, so that's the FAQ in case you want to like learn a bit more about some of the privacy, implications when using something like this. Okay, so that's the hands-on demo. Um, and then I'll just go back to my slides here. So in terms of improvements and feedback, right, Teachable Machine's really useful. It's great. I came up with a list of things that I personally would want changed if like a developer came up to me and asked for feedback, right? So first off, I kind of talked about this, but like the scrolling aspect of it is just one of those small quirks where if you're a new user, you might uh, you might like accidentally, uh, you know, mess up on. Requires square image format, right? Otherwise, it will be cropped. Um, Not all image types are supported. Okay, so for example, like WebP files, we saw that limited to front-facing camera. So, um, so we didn't really notice this, right? Because we're on laptop, and then on laptops, most laptops only have a front-facing camera. But if you were to actually try using this on mobile, which I have, I discovered that you can't actually flip your camera around. You can only ever use the selfie camera. So I think the reason why this is because Teachable Machine originally was developed for laptops, right? It was developed on the laptop interface, not on mobile. Um, so so when they brought it over, they never really added that functionality, but I think it's definitely really useful to add. Because from a real use case scenario, let's say I have my phone. I'm not going to turn my phone around and try to make predictions on the object using my selfie camera, and then I need to like turn it back around again. But by the time I turn it back around again, it's going to be a new prediction. So that doesn't really make sense. So it would be nice if they implemented a rear view camera, and then it cannot detect duplicate images. So with our training data, right, the idea of like having duplication and bias, right? If you have duplicate images, then it creates a lopsided population in your image data, right? Like let's say, uh, like with the fish example, for example, like the Nemos, right? Even though like the Nemos, they were different angles and just different pictures. If, say, for example, I had the same Nemo image duplicated like 90 times, and then the remaining 10 photos are of other fish, right? There's going to be a lopsided problem where there's going to be bias in our data, right? Because our model thinks that is what a fish looks like. A fish must be orange and must have white stripes, right? But that's not necessarily the case. So it all depends on what we use to feed our model, what we use to train our model with. And then last but not least, do not take high percentages at face value. So that goes back to the point with regards to the whole seahorse thing, right? And so here is a screenshot from my phone of using Teachable Machine on mobile. Okay, so um, it says that I'm 100% seahorse. Well, that's not necessarily like that's not true, right? Um, we can't take these high percentages at face value. Like I said before, one of the things with AI nowadays, I think the problem is that it doesn't really know when to say no. It doesn't really know when to tell the user, hey, like what you're asking me isn't actually possible. It always tries to, please the user by providing an answer, even if that answer isn't correct, right? Because to them, giving an answer is better than no answer, but that's not necessarily always the case, right? Because sometimes saying that something is incorrect like is actually true, right? Like in this case here, I'm neither of what is being listed, but our model thinks otherwise. So always double check, always, you know, verify yourself, right? What your model is telling you. Do not just blindly trust it. Okay, so how could image classification fit into your business? So, image classification, it encompasses like a wide variety, right, of different situations, right? Like, does your company utilize infrared or night vision at all? What kind of specialty area does your business serve? Is it like in population estimation? Is it trying to identify different species? Could it not be for animals entirely? Could it be for like other man-made objects like vessels, right? Could you look into improving image quality and trying to eliminate those concerns with regards to, like um, things that could disrupt the quality of your image, like those lighting concerns and what have you, right? The clarity, the blurriness. So yeah, with all that being said, that concludes my presentation and my demonstration. Yeah, so thank you guys all for attending. And then I think um, Layla has a few last closing words, but before that, yeah, any questions? Thank you for your comments, John and Abby. I hope, yeah, I hope you guys like learned something. Um, like with yeah, image classification, its history, how it's used. Um, yeah, and I know like using using teachable machine itself isn't hard, right? Like I'm sure you guys can all figure it out how to use teachable machine. That's not the hard part. I think the hard part is like having conversations about some of the pitfalls behind it, right? Like bringing up that idea about how you need to check it yourself, bringing up how thinking about those situations where you don't expect something to happen, right? The ideal scenario is that we create a model and we have training data for it. But what happens if I give it something it hasn't seen before, right? These are answers we need to think about. Um, and then also placing a huge emphasis on training data as well, right? So with the quality of our model, people always say, how can we improve? How can we do things better? Um, it's like cooking, right? Let's say I was trying to cook a meal. How can I make a meal that's tasty, delicious, and healthy if my ingredients are expired, right? If my recipe, if my ingredients are like, moldy and they're expired and they weren't refrigerated properly, right? How can I expect to create a good meal if I don't have the good ingredients? So that's the same idea here, right? It all starts off with your training data, right? And then we learned about the different factors in which what can quantify good training data, right? It's about using different angles, different perspectives, thinking about the lighting, making sure that there's no kind of, you know, there's uh, there's no class imbalance, right? So each different category has a similar proportion of representation in our images. Okay, so that's yeah. So hopefully you guys found that interesting.